Hello, I'm going to talk about a tree-hops approximation algorithm for stochastic minimum vertex cover in general graphs. This is a joint work with Naveen, Durvasula, and Nika Haghtalab from UC Berkeley. Okay, what are stochastic graphs? They can be seen as a generalization of random graphs where edges are realized with different probabilities. So you are given a base graph G and the probability P sub E for the realization of each edge. Then these edges are realized independently with their corresponding probabilities, forming your stochastic graph or the realized subgraph G star. Now, in the setting that we consider today, we assume that you don't know the realization of the edges in advance. Rather, to know whether an edge exists or realized in G star, you have to query it. And the goal is to find an approximate solution for whatever problem that you study using a small number of non-adaptive queries. In other words, you want to pick a sparse subgraph of your input graph such that by querying those edges, you are able to find a solution with a good approximation ratio. And we compare the approximation, we define the approximation ratio of our algorithm with respect to the omniscient optimal solution, which is a solution that you can find if you know the realization of all the edges beforehand. Some of the problems studied in this setting are minimum spanning trees, packing problems, shortest paths, maximum matching, and the one that I'm going to talk about today, minimum vertex cover. Minimum vertex cover of a graph is the smallest subset of edges that include at least one endpoint of any edge. So if you consider this graph, the red set form a vertex cover of this graph. Now, here are the known results for a stochastic minimum vertex cover. We know that it is possible to get an almost 2 approximation using only n poly 1 over p queries. Here, p is the smallest p sub e, right? The smallest probability for all the edges. Using the same number of queries, you can get a 1.36 approximation for bipartite graphs. And if you allow more queries, which is exponentially 1 over p, it is possible to get 1 plus epsilon approximation for bipartite graphs. We know that n, O of n over p queries is required to get any constant approximation, so these two have asymptotically tight number of queries. For minimum vertex cover, in general graphs, not necessarily stochastic graphs, we know that under the unique games conjecture, it is not possible to get better than 2 approximate solution in polynomial time. So if we are hoping to go beyond this 2 approximation, we have to allow exponential time. We have to allow exponential running time, right? So the question that we ask here is whether it is possible to go beyond 2 approximation using only O of n over p total queries if we have unlimited computational power. So this is just an information theoretical question. How many edges do we have to query to get better than 2 approximate solution? Our answer here is you can get down to 1.5 approximation, almost 1.5 approximation ratio using O of n over epsilon p queries. And as I mentioned, these number of queries are required to get any constant approximation, so it's tight. We also show that little omega of n queries are required to get anything better than 1.5 approximation ratio if you allow only O of n edges to be realized in a correlated way, right? So it means to be able to get better than 1.5 approximation, you have to strongly use the fact that edges of the graph are realized independently. Okay. I'm going to go over the problem again and then talk about our algorithms. So we have our input graph G and a parameter P sub E, which is the realization probability of any edge. Then edges of the graph will be realized independently with their corresponding probability, forming the stochastic subgraph G star or the realized subgraph. Now, the goal is to query a small subset of edges to find a small minimum vertex cover, right? Now, to make sure that the solution that we output is a valid vertex cover, we have to cover any edge that we don't query, right? Because if we don't do that, there's a chance that that edge is realized and the solution that you output will not be valid, right? So to put the problem differently, our goal here is to take a sparse subgraph edge of the base graph, right, such that after we query this edge, right, and we find this minimum vertex cover, it's a good approximation. Okay, what is this minimum vertex cover? It should cover all the edges of edge star, which is the edges that we query and we see that they are realized, and all the edges that we don't query, right? A minimum vertex cover of the queried and realized edges and the edges that are not queried. And the approximation ratio of our algorithm is defined as the expected size of this vertex cover over the expected size of the optimal solution, which is the minimum vertex cover of G star, right? This itself is a random variable because G star is a random graph. Okay. Now that we have defined the problem clearly, let's talk about some simple but inefficient algorithms. Give us some intuition why we have to do better. First, what if we query all the edges? This clearly is not good because your graph can potentially be very dense and you don't want to query that many edges. What if we query nothing? That actually gives us a 1 over p approximation, which if your p is very small, would be a bad approximation, right? And an example here would be if your graph is just a matching, right? And finally, what if we query a constant number of edges for any vertex uniformly at random? This seems a little better than the previous ones, but actually the approximation ratio that you get here is not better than just querying no edges. So we have to be smarter about it. Now I'm going to talk about our algorithms. I will start by talking about two simple two-approximation algorithms, and then see how we can use the ideas here to go beyond two approximation and down to 1.5. Okay, in the first algorithm, we start by taking a random realization of G, right, which contains each edge independently with probability P sub E. Right? So G1 is from the same distribution as G star, right? Because both of them include each edge independently with probability P sub E. Then we take a minimum vertex cover of this graph, which we represent by P, and we commit all the vertices of P to the final minimum vertex cover, which means you don't have to query any edge that has an endpoint here because you will cover it anyways. And that's exactly what we do. Now we are going to query all the edges that do not have an endpoint here. That would be an induced subgraph of G over the vertices that are not in P. Right? After querying these edges, we are going to take a minimum vertex cover of H star, which are the edges that we query and are realized. And then we output the union of P, which is a minimum vertex cover of G1, and minimum vertex cover of H star. This clearly covers all the edges that will be realized, right? Okay, now let's see how this algorithm works for this graph. Okay, the first step is to take our random realization, the random graph G1, right? Let's say after we realize each edge independently with their probability, this is how G1 looks like. So the second step is to take a minimum vertex cover of G1 and commit all those edges to minimum vertex cover. So this is a minimum vertex cover of G1. These will be in the minimum vertex cover, so we don't have to query any of the edges connected to these. So we are going to remove those edges, and these are the remaining ones. Now these are the edges that we are going to query. That's our edge, right? Now, after querying them, it turns out that these three edges are actually realized. So we also take a minimum vertex cover of these edges, the green ones are minimum vertex cover of this. Now, the output will be the union of the green vertices and the red ones that we previously committed to the final solution, right? Now, there are two questions that we have to answer. Why is this a 2 approximation? And why is it the case that you only query O of n over P edges? First, let's talk about the approximation ratio. As I mentioned before, G1, the random realization of G, comes from the same distribution as G star, the actual realization, right? Which means the expected size of their minimum vertex cover is the same, right? So the number of vertices that you commit to the solution in line 1 has exactly the same size as the expected size of the optimal solution. Now we have to see how many edges we add to this in line 3, right? That clearly is also upper bounded by opt because you only add a minimum vertex cover of a subset of the realized edges, right? So putting 1 and 2 together means that this algorithm returns a 2 approximate minimum vertex cover. Now, the second question, why is it that we query only O of n over P edges? This is just a simple application of union bound, and there are 2 points. The first one is that H is actually an induced subgraph of G, right? So there are 2 over 2 to the power of n possibilities for it. And the second point is that none of the edges of H are realized in G1, right? Because if one of the edges of G is realized in G1, then you have to include one of the endpoints in P, right? And as a result, that endpoint will not exist in H, right? So now based on that, we can give an upper bound of 1 minus P to the power of X for any subgraph with X edges being H, right? Because none of the edges of that subgraph should be realized. Now, putting these together and doing the math, we see that with high probability, H has at most n over P edges, which is what we wanted. Okay, now that we prove this algorithm is a 2 approximation and queries at O of n over P edges, I'm going to make a slight modification to it, which helps us get more intuition about how to improve this algorithm and when it performs well. And that modification is that after I query edges of H, I will also hallucinate the edges that I'm not querying to form a subgraph G2. And why am I doing this? Because I want G2 to come from the same distribution as the actual realization, right? Okay, so again, G2 is a subgraph containing all the edges that I query and are realized, and it also includes any edge that I'm not querying independently with probability P sub E. Now the algorithm will return union of P, the same as before, and a minimum vertex cover of G2. Now P and minimum vertex cover of G2 may share some vertices, right? Okay. Now let's have an alternative analysis for this algorithm, see that it gets to approximation. And again, why did we do it? Now, G1 and G2 are from the same distribution, and their minimum vertex cover are also from the same distribution as the optimal solution. Okay, now the alternative analysis. I'm going to start by defining CV for any vertex to be the probability that this vertex joins the optimal solution, which is the minimum vertex cover of a random realization. Now we can see that the probability that this vertex is outputted by the algorithm, by algorithm 1, is 1 minus the probability that it doesn't show up in any of the 2 vertex covers that we took. Because any of these 2 vertex covers come from the same distribution as opt, the probability of this vertex being in S1 would be 2C2 minus CV squared. Okay, now I will define a per vertex approximation ratio, which is the probability of this vertex being outputted by the algorithm over the probability that it exists in the optimal solution, which we see for any vertex, it is 2 minus CV. Clearly, it implies a 2 approximation, but it also tells us that if all the vertices have large enough CVs, this algorithm itself beats 2 approximation. It's even enough for a constant number of vertices, a large enough number of vertices to have large CVs, right? Now, if we think about it, the problem here is if almost all the vertices have very small CVs, we observe that in this situation, your graph is already sparse, so you can query almost all of it. Now, using this intuition, we are going to design a second 2 approximation algorithm which performs better for instances where CVs are small. Okay. Now, the second algorithm is as follows. You start, okay, let me also mention this, that all the algorithms that we design in this paper have a similar framework. You first take a subset P of vertices, commit those to the minimum vertex cover, and then query the edges that are not covered by it, and also find the minimum vertex cover of those, and return the union of these 2 sets. Here, P consists of vertices that have CVs larger than half minus some epsilon. Okay. Again, CV was the probability of a vertex joining the optimal solution. So in line 1, we take all the vertices that have CVs larger than half minus epsilon. Then we take all the edges that are not covered by P, right, which is an induced subgraph of G over vertices that are not in P, and then query those edges. That gives us in HS star, a realization of edge. And again, similar to what we did before, we also hallucinate all the edges that we don't query to get the random subgraph G2, right? Again, G1, again here, G2 comes from the same distribution as the actual realization G star, right? So now we return union of P and minimum vertex cover of this G2. 2 questions. Why does this algorithm only queries of N over P edges? Why is it an almost 2 approximation? To answer the first question, let's observe that any edge that is not covered by P has 2 endpoints, both of them having CV smaller than half minus epsilon, right? Which means this edge itself is covered by the optimal solution with probability at most 1 minus 2 epsilon, right? So this edge has 2 epsilon probability of not being covered by random minimum vertex cover. But I already proved that when you take a random minimum vertex cover, there are O of N over P edges that will remain uncovered, right? Which means you can have at most O of N over P epsilon such edges, okay? So we are done with showing that this subgraph of edges that we query is small enough. Now let's talk about the approximation ratio of this algorithm. Okay, again, I'm going to define a per vertex approximation ratio, which is the probability of the vertex being outputted by this algorithm over the probability of the vertex being in the optimal solution. If the vertex has CV larger than half minus epsilon, it will join the minimum vertex, it will join S2, probability 1, right? So this term for it will be 1 over CV. And if the vertex has CV smaller than half minus epsilon, it will not join P, right? So the only chance of the vertex being outputted by this algorithm is if it is in the minimum vertex cover of G2, which happens with probability CV, right? So for such vertices, this whole term, both probability of V being in the optimal solution and V being in opt are the same, right? So for that vertex, this term is going to be 1. Okay, now let's plot this function. The x-axis is CV going from 0 to 1, and the y-axis is the per vertex approximation ratio, right? Probability of the vertex being outputted by this algorithm over the probability of the vertex being in the optimal solution. We see that for vertices with CV is smaller than half minus epsilon, the per vertex approximation ratio is 1, and this function picks at half, right? And even then, it's upper bounded by 2, which means this algorithm, again, is a 2 approximation. Now, let's compare this algorithm with algorithm 1, okay? So now we are going to also plot the per vertex approximation ratio for algorithm 1. That would be the blue line, right? Because it was 2 minus CV for each vertex. Okay, now when we compare these, we see that the first algorithm has a very bad performance if a large portion of vertices have a small CVs, while the second algorithm has the opposite behavior, right? If a large portion of vertices have a small CVs, the second algorithm is better. An interesting observation here, though, is that any vertex that you take, any CV, right? For any CV, at least one of these two functions is upper bounded by 1.5 plus epsilon, right? You can pause and verify that. Okay. What does this mean? If the vertices were allowed to pick which one of these algorithms or run for them, which clearly is not possible, you would get a 1.5 approximation, right? Why that's not possible, something else that you can do to beat 2 approximation is that run the best of these 2 algorithms, right? You can have a weighted vote between the vertices, right? Weight would be the CV of the vertex, and you can make half of the vertices weighted happy, right? Half of the vertices will get 1.5 approximation, and the other half get 2 approximation in the worst case. We observe by the slightly better analysis that best of these 2 algorithms actually gives you a 1.66 approximation. Okay, it beats half approximation, but it's not 1.5 approximation that we wanted still. To get down to 1.5 approximation, we have to do something more involved. What we do is that we partition the vertices to 2 subsets, right, based on their CVs. And what we do is that we treat these vertices differently, okay? The probability that these vertices be committed to the vertex cover in the first step will be different based on which subset they belong to. For the ones that are in the red area, we treat them as algorithm 2 would treat them. And for the ones in the blue range, we treat them similar to algorithm 1 would do. And we are still able to show that you will query at most O of n over p edges and get 1.5 approximation. I'm not going to go into more details about it, but that's the general idea. Okay. Now, let's talk about whether it is possible to go beyond 1.5 approximation. As I mentioned, we show that if O of n edges are allowed to be realized in a correlated way, it is not possible to beat 1.5 approximation using only O of n queries, right? What does this mean? It means that you have to strongly use the fact that edges are realized independently to be able to beat 1.5 approximation. In our algorithm, we only use the independent realization of the edges to show that the number of edges that you query is O of n over p. We don't use that at all in the analysis of our approximation ratio. So there is some room for improvement here. Okay, now let's also, so talks about some open problems. This clearly is the main open problem here, but some other open problems are about both matching and minimum vertex cover, maximum matching and minimum vertex cover. We know that for both these problems, to get any constant approximation, you need O of n over p queries, right? Now, the question is, what approximations can you get? What are the best approximations that you can get using these many queries? So using the asymptotically tight number of queries, what's the best approximation that you can get? These are the currently best known approximation ratios that we have for matching in general graphs, matching in bipartite graphs, and minimum vertex cover in both these settings. And it's very interesting to see whether these approximations can be improved and to 1 minus epsilon and 1 plus epsilon. Thank you.